Hi, my name is Tom and you are at level 19 out of 30 easy steps to learn everything about Einstein's special relativity. This is the C level for level 19, the one where we are actually going to do some rock climbing. Are you ready? GP, hit it! Hendrik Antoon Lorentz. That's how we Dutch pronounce his name. And he's Dutch. Hendrik Antoon Lorentz. And maybe you've seen the first two parts of level 19. The one which is targeted for all. The one that's targeted at daredevils. And if you click this one, we are going to do some rock climbing. Because we are going to fix the trouble with light using math. In the first A level, we looked at what the trouble is with light and we told you how Lorentz fixed it together with many other people. In the daredevil section, we saw how the Lorentz transformation actually looks. And in this section, we are going to apply the Lorentz transformation. So let's get into it. Remember this simulation. It was, I think, in the A level of level 19. We have two trains. The train on the left has a cannon with a ball in it. It will start to drive and will shoot the ball. We know up front that the cannon or the train with the cannon will move relative to the ground with 10 meters per second. We know that the cannon will fire the ball relative with 20 meters per second, so relative to the cannon. And we know that the observer train on the right will travel 30 meters per second in the opposite direction, from right to left, and that's why it has a minus sign. This is what it looks like. And now try to move your perspective to the ground. Well, we were already in that perspective, right? We as viewers were fixed to the ground. And we saw the ball moving at 30 meters per second because it had 10 meters per second because the cannon was already moving and another 20 when it was shot. So together 30. Now try to change your perception into the perspective of the observer in the train on the right. He will see the ball coming at him 60 meters per second because he's running towards it at 30. So this is Galilean relativity, which makes perfect sense. The trouble with light is if we do the same with light, and here we say, well, it's not a cannon, it's a flashlight, it's not a ball, it's a flash. The flashlight will move relative to the ground 10 meters per second. The observer will do minus 30. And, well, let's say that the light moves at the speed of light for us as viewers, stuck to the ground. Which makes sense, why not? Then we do the animation. And I have to say, this animation is incorrect. I cannot come up with an animation that shows you the perspective from our point of view, the ground, together with the perspective from the cannon, together with the perspective from the observer, and in a single animation. I just can't. And that's the trouble with light, because the trouble with light is that we all think light is traveling at the speed of light. We all get the same number. So if you run towards the light, it doesn't come at you faster. If you run away from it, it doesn't come after you slower. It's always the same. I mean, it just doesn't compute, right? It's so not intuitive. It's a single piece of information that hold me back on Einstein's mountain. I just could not accept that this was the case. Eventually I could, and I will explain why in, I think, level 23, my super level. But this is it. So Lorentz came up with this transformation. We talked about it in the previous section, in the B level section of level 19, with the Lorentz factor, gamma, and the speed of light. And he says, well, if you do this, and you switch perspective from the train to the ground, from the ground to the observer, they will all get C for the speed of light. And I said, well, let's do it. let's mumbo jumbo. Let's do the math. So here we go. We are observer 1, the ground. And our first event is at t is 0, and we switch on the light. And the flashlight will be at x is 0 as well in our world. The second event is maybe 1 second later, and so our t will be 1 second. And what will be the x of that moment for the flashlight, the flash? It will be exactly, 299792458 meters away, because, it was traveling at the speed of light. Let's check it. Speed of light, the change in x coordinates, divided by the change in time, meters per second, delta x over delta t, is, it's the speed of light. So, we're good for observer 1. Let's see observer 2. And observer 2, let's do that. Observer 2 is the train on the left that had a velocity through our eyes. We are observer 1 with 10 meters per second. The first event for that observer will be the same, because at t is 0, all observers in Einstein's special relativity, they sync their clocks and they are in the same place. So, that's easy. How about event number 2? Well, let's use the Lorentz transformation, shall we? The Lorentz transformation is that I can calculate the coordinate of event 2 through the eyes of observer 2 by using this equation. And I can also calculate the time of event 2 through the eyes of observer 2 using this equation. And the speed of light, of course, is the difference in x divided by the difference in t. So let's do that also for observer number 2. It's the x coordinate of E2, the event 2, minus the x coordinate of event 1 through the eyes of observer 2, not 1, divided by the delta time. Here it is. And because x and t of the first event are also 0 for observer 2, they get lost. They're gone from the equation. So it simplifies into x over t for the second event. Let's put in the Lorentz transformation equations for x for the second event and t for the second event. Those are the equations just a few lines up. If we do this, we get this one. It's a long equation, but this is what we are going to divide. So this is equation number 2. I repeat equation number 1, and I will repeat equation number 2. So here we are. So now let's do a little bit more work on the second equation. We are going to divide both ends by the time of event 2 through the eyes of observer 1. And then you see that t will cancel out here and there. So we end up with this equation. The x over t minus v divided by between squares 1 minus vt v over tc squared. There it is. Now put equation number 1 into equation number 3, because we have x over t through the eyes of observer 1 in there. So, and that's c. That's the velocity that observer 1 saw. So we put in c. So we get this one. Now let's do some mumbo jumbo. We're going to apply both parts with c. We get this. Oh, and now the stuff between brackets cancels out and we get c. Et voilà, the French say. There it is. English people will say. Daar is het. We Dutch say. So, we have proven that the speed of light observed by observer 2 is also c. And you can do this easily for any observer with any arbitrary velocity relative to the ground, because that velocity just drops in the equation. It has no effect whatsoever, and you will always get c. And that was what Lorentz was after. Fix it by some transformation that will make the speed of light always travel at c for all inertial observers. I want to thank you for watching and hope to see you at level 20. GP, hit it!